Hello, hello.
Good morning, Professor. I was scared for a second. Nobody show up, so I said, "Damn, I'm
Yeah, no.
gonna miss the quiz. The quiz grade."
No, I'm actually kind of surprised that no one else is here.
Yeah, I'm surprised too.
Give him a sec. Here, you can go ahead and. There we go. Got Josh at least. So, y'all. Whoops, let me edit that. But I'm wanting y'all to just practice that diagonalization really quick with a nice little 2x2.
Extra points or what, Professor?
Do what?
Extra points or what for being
No,
here?
you just
So,
don't. You actually get a
so,
grade versus a zero.
so I have a question for the one that you're asking right there for the poll everywhere. We have to answer for P, B, or P inverse.
Uh, D, just D. I'm not going to ask you to type in P as well. That would just be extra time. I want you to see if remember how to quickly find D. And then as a group, we'll go through P, finding P for this. So Nabari's here. We're just late today. I was a little late to join anyway. It's Friday. Here we go. Everyone's slowly coming in. Actually, wait a second. Check this. That one's reasonable. Yep, I'm not going to change that matrix.
We do end up with square root and fraction, you know.
So just like how you do it in web work. Type it in web work, type it in here. Let's see, Chevy joins.
So type it the row or the columns.
The row. So same way we've typed in here, look at Zoom. If I was wanting to type in 2, 3, that matrix 2, 3, 1, 1,
It'll be 2, 3 in parentheses.
wouldn't be in parentheses. So we do that bracket notation.
Yeah. Okay.
It has been a little while since we've done it. That's how we would type it in right there. Yep. Actually, I think I have that. Matrices. Should be. All right, I'm just going to give you all 2 more minutes, just about. I know some people are straggling in kind of late. I got to the class later than I usually do as well. It's just today, apparently.
A square root, we write it as SQRT, right?
Mm-hmm.
And then the number in parentheses, or
Yep.
just square root.
Yep. You got it. You know, I wrote this question. I forgot how long it's been since I've kind of made y'all type in stuff like this, whether it be in web work or for like a daily quiz. So yeah, thanks for asking this question so I can remind everyone. So again, this is a daily quiz problem. Oops, I didn't put that daily quiz. Dang. Daily quiz. Why is that? Sorry, that question is so funky. All right, now the question's done. The work is still the same though. Find that diagonal matrix D that diagonalizes A, i.e. that makes A similar to that diagonal matrix D. Which we've done the process a few times now. I do not want the matrix P. I do not want the P, I just want the matrix D. Now I got yours in.
I don't even know if I did it correctly. As in, if I wrote it correctly or not.
Yeah, I know what I was trying to write, but I don't know if it came out the way I wanted it to.
Well, a good thing is I can at least interpret a little bit better than a computer. Computer's got to do it as is. But let me see. I see the answers coming in.
I submit to
So Josh, make sure you're writing it as a matrix. So I'm going to say Chevy Elliam, I see yours. Elliam, the only thing would be that you use parentheses instead of square brackets, like we talked about. But I see what you're writing. And you're good. I'm not going to tell you whether it's right at this moment, but I see what you're writing.
Okay.
Same for you, Chevy. Let's see. We got everyone's in. 5 of us today. All right, so I'm going to go ahead and lock it. It looks like most of y'all got it in some form or another. So I'm going to lock answers just in case you're trying to type something in. I'll give you 5 more seconds. You know, a couple people have been changing. 3, 2, 1. Locking answers now. All right, so yeah, most of y'all got it correct. It would have looked like, depending on what you found your eigenvalues to be, what order you want to put them in, 3 minus the square root of 13 over 2, 0, 0, 3 plus the square root of 13 over 2. You can enter in that as your D, and technically, you could also have done 3 plus square root of 13 over 2, 0, 0, 3 minus square root of 13 over 2. Either of those would work. Either of those would be a diagonal matrix D that is similar to A. And so we say it diagonalizes A. Right? And just, again, how we get it, but just for brevity's sake, calculate the determinant of the A minus lambda I matrix. So it'd be 2 minus lambda, 3, 1, 1 minus lambda, 2 minus lambda, 1 minus lambda minus 3. So you'd have 2, and then what? Minus 3 lambda plus lambda squared minus 3, which gives you what? Lambda squared minus 3 lambda minus 1. Is that right? Yeah. Because then you would use your quadratic formula. Negative 3 plus or minus square root of negative 3 squared minus 4 times 1 times negative 1 all over 2 times 1, which gives you that 3 plus or minus square root of 13 over 2. So those are your eigenvalues, and all the theory that we've been building up recently is that I can always write any matrix as a diagonal, or it can be diagonalized in such a specific way where my matrix D, whatever my eigenvalues for my matrix are, it just takes those and puts it along the diagonal. And that's mainly what I was looking for, is you to remember that for this question. Okay. Any questions so far?
Yeah. Okay. So for this one, you were just asking just to do all of this. That's all.
Yeah. And then that's why we get our answer, because of our 2 eigenvalues are negative, or 3 minus square root of 13 over 2 and 3 plus square root of 13 over 2. We could use those to create that diagonal matrix D as in all.
Okay. Okay. I got it now.
Any other questions? All right. So I don't want to find the P for that. That's going to be crazy. So I'm going to just talk about some theory. We're going to do another example at the end of it and do a proof in class, not watch a video of that James guy doing a proof in his lectures. We're actually going to do that. So just a couple language things that I wanted to make note of, especially for the homework, because we haven't used this specific type of language before, though it's not really anything of consequence. Whenever you see this statement, or it's asking if it's diagonalizable over the real numbers, or the C, which is the complex numbers, but let me write this all out. So diagonalizable over the real numbers. When we say diagonalizable over the real numbers, that just means that whenever we get our eigenvalues and our eigenvectors, they only involve real numbers.
So that means that whenever you have an eigenvalue of I, that means it's not diagonalizable.
Over the real numbers. Because when we say over the real numbers, we're restricting ourselves to saying we can only use real numbers. So hold on, I can pull out our lecture notes and you can go over an example. But let me finish both of these statements. And maybe after that, and I give the example that can help clear it up a little bit. So diagonalizable over R means our eigenvalues and eigenvectors are only real numbers, no imaginary numbers in there. If we see diagonalizable over C, and this is our bold face notation for C. I don't think I've introduced this before, but it represents the complex numbers. So that C always represents complex numbers. You're going to see that in any class that you go to. That's a very, very, very common symbol to represent that set. And when we say diagonalizable over the complex numbers, eigenvalues and eigenvectors can be imaginary numbers. Let me see if I have, yeah. So I'll give you a second to finish writing that down. That's what that language means. You'll see it at the bottom of a couple of your webwork problems. I know, Eliam, you're done with them already. So if you're wondering where that language comes from, this is what they're talking about.
Got it.
Give me a thumbs up if you're done writing so I know to move on.
I'm done writing.
Thank you. Cool, got 3, 4. All right. So for example, we had this matrix last Friday, actually. It was A is 1, 5, -3, 1. And we ended up finding that my eigenvalues for this matrix are they 1 plus I squared of 15 and 1 minus I squared of 15. We also found eigenvectors associated with those eigenvalues for that first one that I have listed here, 1 plus I. Let me make sure I'm getting my notes correct. We did 1 plus I, so its eigenvectors look like, or anything in the span of I squared of 15, all of that divided by 3 and 1. And then eigenvectors for the other one were negative I squared of 15 over 3 and 1. Okay. This is matrix that we did these calculations for last Friday. And I could use these to, again, make a diagonal matrix D and a matrix P to diagonalize A. So my D would be, let's say, 1 plus I squared of 15, 0, 0, 1 minus I squared of 15. And my P would be I squared of 15 over 3, 1, and then negative I. Okay. So then my question for you is this matrix A diagonalizable over the real numbers?
No.
Yeah, the answer is no. We can diagonalize it, but to do so, we have to dip into complex numbers. So is it diagonalizable over the real numbers? Answer is no. And I don't have a great place to write below it, but if I would have instead asked, is it diagonalizable? I want to erase. Over the complex numbers, what would your answer be to that question? Is it diagonalizable over the complex numbers?
Yes.
Yeah. Because I'm still able to diagonalize it. I'm still able to find eigenvalues in enough eigenvectors. So I can create that matrix D and that matrix P to then show that this matrix A is similar to some diagonal matrix D. And so that's just what that language means, really, whether or not can you use only real numbers or do you have to also go into complex numbers? Okay, so questions? All right. So the next thing I was been talking about, and I guess just to motivate it, everything again really quickly. Kind of the theme that I've been trying to keep for us when we're building all this theory is we're trying to be able to find solutions to a system of equations. Okay? Because there are many, many different areas of science, social sciences, statistics, where you can boil down the question and the data you're looking at to a system of equations. And our goal is to find solutions to these. Okay, and one of the questions we've always been asking is there a unique solution? Are there more than one solution? And by the end of class, we're going to also say, well, when there are no solutions, what is the best looking solution, called the least square solution? That's here in a week and a half. Okay? So we had started with saying at the very beginning, we can define inverses of matrices, right? And say, hey, if I multiply both sides of this equation by that inverse, then I can find what those solutions are. Because anytime I take any matrix A multiplied by inverse, it gives me the identity. We said, if the inverse exists, then we're going to have a unique solution. But we kept seeing that finding an inverse was not necessarily an easy thing to do. Right? We were doing it with just 3x3 matrices at most. Maybe I think I maybe gave you a 4x4 in the homework. But when you get to larger and larger matrices, this is a very, very, very tedious thing to calculate, and it takes a ton of time. So one of the questions we asked is, how do we know if A inverse even exists? Does anyone remember what we calculated?
Determinant?
Yeah. As long as the determinant of A was non-zero, we were guaranteed that A inverse exists. Right? And that was our cue. Okay, yeah, we had to put in a little bit more work before we go try and find the determinant. But this at least allowed us to figure out whether or not we could, find the inverse. That allowed us to figure out whether or not we could find the inverse. Okay? And then one of the things that we've been talking about with this diagonalization, okay, cool, we have this new way to classify some types of matrices. It's diagonalizable. If I can, a matrix A is diagonalizable if I can rewrite it as a matrix P times the diagonal matrix D times the inverse of that matrix P. And I've told you that this will translate into helping us solve this system. AX equals B, because I'll be able to rewrite this as PD P inverse times my vector X equals to B. But there's one small issue that we have. Because we're trying to get away from calculating inverses. What do I still have there? What did I just point at with that green arrow?
Inverse?
Yeah, another inverse. Right? Well, Aaron, you were trying to tell us that we're getting away from having to calculate inverse. Find a smart way to be able to solve this. But I still have to calculate an inverse. And as you do in the homework, right? Once you find your matrix P, you still have to go through some matrix P, you still have to go through some process to find it. Now we can mess with that equation some and see, okay, well, maybe if I find P, I can solve this equation relatively easily. So we have PD, the inverse X is equal to my vector B. Well, if we just assume the inverse is known, if we already have it, it's relatively simple through just some matrix calculations to figure out what that value X needs to be. Right? So I can just take both sides of this equation. If I already know what P inverse is, I can multiply by it. And again, any matrix times its inverse results in what particular matrix?
Identity.
Yeah, I heard Khalid saying it too, identity matrix, right? Which means on that left-hand side, this just leaves me with a diagonal matrix times that P inverse. And then, whoops, I didn't write it on this right-hand side. Because I want to multiply the left-hand sides of both equations by that P inverse. That's kind of important to have. So then I have, now that this diagonal matrix, D, times the inverse of P times the vector X is equal to the stuff on the right-hand side. Now there's also this nice property that if D is diagonal, then that inverse of that diagonal matrix is super easy to calculate. In fact, there's not really much to calculate. I can already tell what the form is. And we're going to go with that on the next slide because I don't think I've fully covered it. I might have mentioned it. I wanted to mention it last week. But then if it's super easy to calculate, super easy to find, I can multiply both sides by the inverse of D. And then this leaves me with P inverse times X equal to whatever the inverse of D is times the inverse of P times the inverse of B. And then I can also multiply everything by a P on that left-hand side. And I see just looking at these generally, as long as I can diagonalize a matrix, I have this caveat of I can quickly calculate the inverse of this matrix P, I can get what my solutions are going to be. They're going to be a unique solution. There's only one solution I'll be able to get. Okay? So this is why we want to go through this, because again, we don't have to calculate an inverse of an entire matrix. We have to calculate now an inverse of this special matrix. There's two things I want to kind of harp on. And the first thing is showing that that diagonal matrix, the inverse is very, very simple to calculate. Okay? But this second point, which I'll kind of block off in yellow, we actually are going to be setting up the theory to say, okay, well, I can actually create a nice matrix P, as in Paul, right, that P, such that P inverse is actually a super, super, super easy thing to calculate as well. This is why we care about diagonalizable. It feels like we're having to go through this crazy route, but it saves us so much work. Once we build up this theory, build up our tools in our workshop, and we now have this process of building our chair. I don't know. Okay, yeah, it took a while to assemble all the tools, but now that we have them, it's going to be really easy to make that chair in a very quick amount of time, a very short amount of time. Okay. So like I said, I want to get on this blue square, the yellow square where we kind of find that P inverse. That's kind of what we're building. That's what we're going to be building up through to next week or through next week. But any questions so far? If not, give me a thumbs up. All right, I saw most people give a thumbs up. So, we're going to let D be a diagonal matrix, and our goal is to find what the inverse of this thing is going to look like. And it's a very, very, very easy thing, because remember, a diagonal matrix is something like 3, 4, 5, where all my non-zero entries are on the diagonal, and I have zeros elsewhere. Okay. I want to figure out, okay, what matrix should I put in here? Should I multiply it by, which will end up being my D inverse, such that I end up with 1, 0, 0, 0, 1, 0, 0, 0, 1. Well, I just take each of those diagonal entries and find its multiplicative inverse. Find out what I need to multiply it by to get to 1. And that is what's always going to give me my inverse. Because anytime I do this matrix calculation, right, do the first row times first column, it's going to be a 3 times the 1/3, which gives me a 1, and the rest of them I'm multiplying by zeros. If I take 3, multiply this first row, multiply by the second column, I'm going to take a 3, multiply it by a 0, that's still 0. And I take these 2 zeros and multiply it by everything else in that column. Okay? So as long as my entries are non-zero, as long as my diagonal entries are non-zero, I'll always be able to find the inverse super, super easily of any diagonal matrix. So when we've been going through this diagonalization process, where we've said, okay, this diagonal matrix will be my eigenvalues all along my diagonal, the zeros elsewhere, then the inverse of this diagonal matrix is going to be 1 over each of my eigenvalues. So that's supposed to be a 2. Keeps going, 1 over lambda n, zeros elsewhere.
And we would find this, we would find the inverse of D to do what?
So then you can figure out what the solutions are supposed to be. Good question. Right, keeping in general, we said as long as we can diagonalize D, or diagonalize our matrix A, so write it as matrix P, a non-singular matrix P times the diagonal matrix times the inverse of that non-singular matrix, right? We can then see that just through manipulation at a general level, we're always going to have a predictable form of what my solution is going to look like. So then, as long as I can compute these parts of this matrix A, I always get the solutions to this system. Good question. Right? And again, why do I have to have non-zero eigenvalues to be able to find the determinant? Or sorry, the inverse. I have to have non-zero eigenvalues.
Because then you would, 1 over 0 is just undefined.
Yeah. If any one of those eigenvalues, lambda 1, lambda 2, whatever, were 0, well, then I would say through this process, the inverse for that entry would have to be 1 divided by 0, which we know innately, inherently shouldn't happen, right? We can never divide by 0. But also think about it like this. What is the determinant of the diagonal matrix? What is the determinant of that diagonal matrix?
The numbers along the diagonal, the sum.
That was one of the shortcuts that we found for calculating determinants, right? As long as I can either see it as a diagonal matrix, or reduce it to just all diagonals, or even an upper triangular, that determinant ended up being the product.
So none of the lambdas can be 0 in this case for
None of the lambdas can be 0 for us to get a unique solution. Because, like we said, I think we have it. Where did we write it? Or maybe we just mentioned it. No, there it is. How to know that we find the inverse of a matrix? The determinant's got to be non-zero. So if I want to find the determinant of that diagonal matrix D, that's just the product of all of its diagonal entries, which means that I want that product to be non-zero, which means each one of those eigenvalues can't be 0. So each of those eigenvalues must be non-zero for us to have a unique solution to the system. There's also another really, really cool observation we can make about determinants if we assume that this matrix A is diagonalizable. But I'm going to stop myself there. I'm not going to keep talking. Questions? I know, Elliot, you keep asking, so that's awesome if you got more and more, but the rest of y'all, any questions so far? Are you following along? Give me a thumbs up if you're following along, but if not, please ask a question. Don't be afraid to be the dissenting. I need you to repeat that. All right. So let's get to the observation that I was telling us that we can make. Well, if D inverse exists, then we're going to have a unique solution, which means then also A inverse should have to exist. Because we had that theorem, if the inverse for that system AX equals B, if A inverse exists, then that system had a unique solution. I'm just writing it out. So you see, you don't necessarily need to write this down for this, right? If A inverse exists, then we have a unique solution. Well, that means, again, that determinant of A had to be non-zero. But if A is diagonalizable, that means I can rewrite this as the determinant of P times D times P inverse. And we had this wonderful property with determinants with matrix multiplication. The determinant of the product of two matrices is the product of the determinants. So this is the same thing as the determinant of P.
Okay, wait, Professor. So first, so you're saying find the inverse of D, but also find the determinant of A, which is the determinant of P times D times negative times
So
inverse.
I was just reminding everyone, right? We just needed we needed the determinant of A to give us to be non-zero to get a unique solution.
Mm-hmm.
That was one of the things we built on. I'm showing you that actually we don't need just the determinant of A. We need the determinant of something else, and I'll show you kind of where it gets to. I might have done a bad job of setting it up, but it should work itself out once we get this calculation done.
Okay, so I have a question. You said the determinant of the product of two determinants? I'm
Here
confused.
was a property that we had written before when we were doing determinants. I did use some fancy math language to describe it. But the determinant of A times B is equal to
Determinant of
A
determinant of B.
times determinant of B. So this is what I was referencing, Chevy. Yeah, in retrospect, I probably said it in the, hey, I get to inflate my ego because I can use a lot of crazy math language, but this is what I was trying to say.
Okay, that makes more sense.
Awesome. Yeah, thank you for asking the question then. So essentially what this is telling me is anytime I'm multiplying matrices together, I'm calculating the determinant, I can split the determinant calculation over the products. Right? So that's what we're doing here. When we have determinant of P times D times P inverse is the same thing as the determinant of P times the determinant of D times the determinant of P inverse. Okay. And then we also had another property. In that the determinant of an inverse, so the inverse of some matrix A is just 1 over the determinant of A. Another little property that we mentioned, we kind of saw, but it's more of a tool used in proving than something we really ever want to calculate. So that's why it's mentioned, kind of never brought up again, but this is where it comes in handy. Because if I take that equation that we have a P inverse, determinant of P inverse, which means this is the determinant of P times the determinant of D times 1 over the determinant of P. What does that leave me with? Because remember, the determinants come out to be a real number. So I have a real number times another real number times 1 over a real number. What does that simplify to?
Wouldn't that leave the determinant of D? Oh, you're dividing it.
Yeah,
Wait,
no, you're right. It leaves the determinant of D, right?
Oh, okay.
You're absolutely right. I'm multiplying by the determinant of P, P as in Paul. I'm going to say Paul. Maybe that'll help differentiate D and P, especially over Zoom. So I have the determinant of Paul times the determinant of Dan times 1 over the determinant of Paul. Well, I'm multiplying by the determinant of Paul and I'm dividing by the determinant of Paul. Cancel each other out. I'm left with, oh gosh, the main result, that is equal to the determinant of that diagonal matrix.
So the determinant of A is the same as the determinant of the diagonal?
Mm-hmm.
Okay, but I understand all of this, but I want to know, once we find this, how can we use this information? I know you said it before, but
So then, yeah, here, let's wrap it up because that's a great question. That is a great question. We said we build these diagonal matrix Ds where everything along the diagonal is my what values?
lambda.
Yeah, my eigenvalues. And we also established that then the determinant of those matrices, where was it? Back on that last page, the determinant of that matrix D then is the product of just all of my eigenvalues. So for whatever my eigenvalues are, however many I have, their product, it actually turns out that the determinant of your matrix A is always just the product of your eigenvalues. And again, that observation that we made, we want a D inverse to exist, meant that we had to have non-zero eigenvalues. Well, that's because it's also the determinant of A, and we wanted the determinant of A to always be non-zero to get a unique solution. So we've actually done the proof of this theorem that I'm about to write out. So if an n by n matrix, well, that's not right. So the system AX equals B has a unique solution if all eigenvalues of A are non-zero and A is diagonalizable. I won't be able to fit in there. I have to go to new line. So this is just another place that, okay, we go through this process of calculating eigenvalues, and I show you when we first learned about it, I told you they kind of show up everywhere. This is another reason why we like to calculate eigenvalues, because not only will it give us a way to diagonalize these matrix, and we said if we need to compute like this same matrix multiplied over and over again, it shortcuts that for us. But it also tells us, these eigenvalues tell us whether or not we're going to have a unique solution. They're really, really useful. And there's other different uses of it.
And you only have a unique solution if the eigenvalues are non-zeros, right?
Yep.
Okay.
And A has to also be diagonalizable.
So that it has a P and a D. That's what you mean? I mean, once you find the eigenvalues, you have a D, but now you would have to find the P, which is your eigenvectors, right?
Yes. But I think, do I have the matrix anymore? No. I think we even had an example where our eigenvalue, one of our eigenvalues was 0. Have it here. No. So you can have an eigenvalue of 0. I know we've calculated a matrix with 0. This is just, again, wrapping back in why eigenvalues, even if we're just trying to keep to this idea of solving linear systems, solving these AX equals B's, why still calculating these eigenvalues is useful. It gives us information about our solutions. Sorry, go ahead, Eliam. I know you're about to ask a question.
Oh, so if one of your eigenvalues is 0, it means that it's not diagonalizable.
Not necessarily. You can still diagonalize it, you just won't have a unique solution. So you can diagonalize matrices that if you threw into a system won't have a unique solution, will have free variables in them. It's just that if you can diagonalize and all of your eigenvectors are non-zero, then you know you have a unique solution. Well, good questions. Any other questions?
Yeah, could you go back to the past slide, the one before?
Yeah, so let me go here.
Yeah. So once we find all of this, that means that we've basically found out what P times D times P inverse is.
What do you mean, found out what?
The determinant of A being equal to the determinant of D.
So we don't, for this proof at all, we don't need to know what P or D are specifically. This is just a general, right? And the motivation for this proof was essentially, motivation for all this is essentially a proof for this theorem that I wrote here. right? If you're considering a system, AX equals B, you know it's going to have a unique solution as long as you satisfy two conditions. It's diagonalizable, and all the eigenvalues are non-zero. So if we prove this, we would start with, okay, it's diagonalizable, which means I can rewrite A as P times D times P inverse. And then we, from there, show that that determinant of A ends up becoming that product of the eigenvalues. So as long as the product of my eigenvalues is non-zero, that means my determinant of A is non-zero, which meant A inverse exists, which then meant we had a unique solution. Do I need to write all of this out, or are you following along?
No,
I
you
know
good.
I'm saying a lot.
No, you good. You good.
Okay. How about everyone else? How are we doing? Oh, dang, it's already 150? Or 250? Wow. All right. Well, Fleet at least responded. Thank you. All right, so I do want to write two quick theorems. First one, and this is whether or not we can actually diagonalize. So similar, in what I was trying to set up was another good question to ask is, will we always be able to diagonalize, and will we always be able to know if we can diagonalize? Right? Same process as when we were trying to set up inverses. Can we find an inverse? Do we know when we are able to find an inverse? We can ask the same two questions for diagonalization. Will I know if I can find one, and then finding it? So this theorem, if a square n by n matrix, A has n distinct eigenvalues, then A is diagonalizable. Right, so this means I don't have eigenvalues with multiplicities. I end up getting n eigenvalues, and each of them are different. And n is matching up specifically with the number of rows and columns of this matrix.
So no multiplicity and no zeros.
So this one doesn't care about zeros. We don't want zeros if we want a unique solution. If we don't care about having a unique solution, our eigenvalues can be zero. But let me go ahead and write this out real quick, this last theorem, then I'll take more questions from you, Ellen, because I know we're already well over time. We can actually relax this condition a little bit more, because it doesn't have to, you can diagonalize some matrices that don't have distinct eigenvalues. I think we actually did one on Tuesday. So we can actually relax that condition a little bit enough. So a square n by n matrix is diagonalizable. If and only if your matrix A has n distinct eigenvectors. N distinct eigenvectors. So these two theorems, this first one, where I'm putting this blue star, is usually what we look for, right? If I can go ahead and say that I have n distinct eigenvalues, then I know I can diagonalize it, and it's worth going into investigating and finding out, okay, that diagonal matrix D and the matrix P, the Hall matrix. However, that's not always going to be the case, because there are some matrices that are diagonalizable but don't have n distinct eigenvalues. So it's a good way, what we call a sufficient condition. For the most part, most diagonalizable matrices will have n distinct eigenvalues. However, that's not always a necessary condition to have diagonalization. That second one is the necessary one. And as we saw, having n distinct eigenvalues doesn't mean there aren't n distinct eigenvectors. We can still have, again, the example that we did last Tuesday, I believe, where we had multiplicity of an eigenvector. Notice it's, even though we had multiplicity of 2, the eigenspace was to span by 2 vectors, and that gave me 2 linearly independent eigenvectors, which then I can throw into P. I did have 2 examples, but I'm over time, so I'm going to have to stop there. Questions?
Yeah, just one question. So basically, if the first theorem doesn't work, you have the second theorem.
Yeah. So, yeah.
And a distinct eigenvector is what?
So different
Linearly
eigenvectors.
independent?
So if you're,
So you can have the same eigenvector twice.
yeah, pretty much. You can't repeat an eigenvector. So for, where is it? You can have, there's this example that I was going to try to do, or at least depict, 2, -3, 1, 1, -2, 1, 1, -3, 2. This is an eigenvalue of 0 and an eigenvalue of 1 with multiplicity 2. However, this is diagonalizable because if I look at lambda being 1, I find its eigenvectors. It's everything in the span of the vector 1, 1, 1. For lambda being equal to 1, all of its eigenvectors are in the span of 3, 1, 0 and -1, 0, 1. Which then these 3 vectors would be what I use to construct my P. So my D would be 0, 1, 1. And my P would be 1, 1, 1, 3, 1, 0, -1, 0, 1. So we didn't have 3 distinct eigenvalues. We only had 2 distinct eigenvalues, 0 and 1. But we can still diagonalize it because I'm able to have n distinct eigenvectors. I have a 1, 1, 1, I have a 3, 1, 0, and I have a -1, 0, +1. The counterexample I was going to give was 2, 0, 0, 0, 4, 0, 1, 0, 2. And this has eigenvalues of 4 and 2 with multiplicity 2. But if I look at what spans those eigenspaces in your eigenvector basis, it would have been 0, 1, 0 and 0, 0, 1. So if I went to try and construct that matrix P, I wouldn't have 3 distinct eigenvectors. So distinct means it's not some scalar multiple of another. So my P in this case cannot be 0, 1, 0, 0, 0, 1, 0, 0, 2, right? Just taking a scalar multiple of that second eigenvector. That won't work. That won't give me a correct P. That would be diagonalizable. In fact, we can even see from that matrix, because I have a row of zeros, its determinant is going to be 0. It won't have an inverse. It won't be non-singular. All right. I am way over time, and I've said that now like 4 or 5 times. Thank you all for sticking with me. I'm not going to do any more material. I can answer questions. I'll keep the recording going, especially if you have something you have to do right after this class. You're welcome free to go to it. Check back in on the recording that I'll have on YouTube up here in a few minutes. Questions?
We're gonna have videos for next week?
Yep, they're already ready. They just won't open up until midnight tonight.
Yeah, got it. All right, Professor, you have a good weekend.
Yeah, thanks. You do the same. Josh, Leona, Khalid, you good? Only on the left.
Yeah, I'm good.
We have one question.
Yeah.
So for both classes, the homework isn't that challenging, is it, right?
Okay. Awesome. I mean, in calc, shit, what did we cover this week? Critical points. I don't know. If you're feeling comfortable with derivatives and you feel confident in your finding the zeros for functions that you had like in pre-calculus and algebra, it might feel tedious and a little time consuming, but it shouldn't be hard. And in this one, for linear, it's about just diagonalizing. So finding these eigenvalues and finding the eigenvectors to then make your matrix D and your Dave matrix and your Paul matrix, your D and your P.
Okay. I was supposed to set up a Zoom call, but I never got the opportunity to. I'll just set it up next week.
Okay, you sure? I mean,
Yeah.
I can just stay in here for a little bit if you've got time.
Hmm.
Recording.
No,